All right, welcome to my lecture on the binomial distribution. Um, and let's get started with an example. Okay, and I'm going to have two examples here. Okay, so let's get started. So researchers want to study the effects of an experimental research. Maybe that's a vaccine on N mice. Okay, and what they record here, so in my first example, I'm just going to have 3 mice so we can work out what's happening. And later we're going to answer this. With more mice. Okay, so we're going to first do a small example, then we're going to do maybe like 10 mice or something like that. Okay, so we want to study the effect on N mice. The researchers are interested in the number of mice that die out of N. And we're going to have some assumptions. Okay. So our first assumption is that the outcome of each mice is independent of the other mice. Of each trial is independent of the other trials. So that is to say, one mice does not affect the other mouse's outcome. That seems reasonable. Okay. Okay. The second assumption is that there is a fixed probability of P of death. And I want to emphasize that that's fixed, and that's for each mouse or each trial. So let me write trial because that's the more common term here. Okay. Okay. And now let's work out our example. So example is we're going to have just 3 mice. And let's assume the probability of death is 20%. Okay. And now we are going to define our random variable. And the random variable is the number of mice that die out of N. Now I'm going to form this table here, okay? And we're going to have the outcome X. We're going to have the event in S. We're going to have the number of ways S occurs. Then we're also going to calculate P of X, okay? Now, I could have that no mice die, and that would be the event of live, live, live for each of the 3 mice. I could have that one mouse dies, so I could have a death, then the other two live. And D stands for death, L stands for live. Okay. I could have live, death, live. So the first mouse dies, the first mouse lives, the second mouse dies, and the third one lives. That's that last outcome. Then I have one more outcome. So I could have the first one lives, the second one lives, and the third one dies. Okay. Then I can have two. So this would be the event. Let's put some bars here. Okay. This would be the event. The first one dies, the second one dies, the third one lives. I could have the first one dies, the second one lives, the third one dies. I could have that the first one lives, the second one dies, and the third one dies. Then I have this last outcomes of 3, so that means everyone dies. Death, death, death. Okay, and let's go through the number of ways this occurs. Okay. One more thing that I'd like to note is that the events in the sample space, because X is counting deaths, we either count things as live, as life or death, a binary operation, one of two outcomes. And that should have been noted in this assumption. So let's add that in. So the third one is that there is only one of two outcomes. And we can generally just call these outcomes success. That's what the random variable X counts, the number of successes. And here I'm calling successes death. Okay, so success is relative. And, or excuse me, or failure. And here failure is life. Okay. So these are assumptions, and let me put a fourth. This is optional. X is going to be the number of successes out of n trials. Okay, I don't think that fourth one is listed in the book, but it's generally understood that X, the random variable, is the number of successes out of n trials. So if you replace success by death, X is the number of deaths out of n equals to 3 trials, or 3 mice. Okay, so number of ways things occur. Here there's 1. Here there's 2. Oh, excuse me, can't count. And speaking of counting, there seems to be like 3 types of mathematicians: those who can't count and those who can't. So counting's hard. Okay, so there's 1 there for x equals 0. There's 3 here. There's 3 here. And there's 1 here. Well, these numbers are very interesting to me. I have 3 outcomes here, and I'm placing. So let's look a little closer. Let's look at this one. So there's 3 here, and I have 3 spots. 1, 2, 3. I want to place 2 indistinguishable objects. That is death. And I'm placing death in 2 out of those 3 places. But if I were to distinguish the deaths by a color or by a name, maybe one of them was Jack and one of them was Julian, the death of Julian here versus Jack here is the same outcome. Okay. So if I were to look at this outcome versus this outcome, death is indistinguishable, meaning that the order here I'm choosing the orders, I'm selecting positions, but the ordering, distinguishing death by a color, as I did here with a blue and one black, indicates that the order doesn't matter. I don't actually care about the color distinguishing the deaths. I just care about how many there are. So that indicates to me it's a combination because these two written here are the same outcome. So I think I have three objects because there's n equals to 3. So I'm going to have 3 choose 2. And that is in fact 3. Let's see if that works. There are 3 positions, after all, 3 trials, and I want to place 1 success. Let's look at this. I think 3 choose 1 is indeed 3. Okay, so great. Then this is 3, and I have to place 3 deaths, so that's 3. This is going to be 3 choose 0, which is again 1. So this seems to work perfectly. Okay, and I'm just going to note, in general, if there are n trials, and x successes, then this outcome occurs in n choose x ways. Okay, and let's calculate a probability for one of these. Okay, so let's calculate probability x equals 2 here. This seems to be saying let's calculate probability that the first is death and the second is death and the third is that the mouse lives. So that's one outcome. Or this could occur by having the first be death and the second lives and the third equals death. So here, instead of writing all the numbers out, I'm just putting underscores to indicate it's the same thing. Okay. Okay, so that's one outcome. Or there's one last outcome, which is that the first so I said I just indicate that with an underscore. The first is life, it lives, and the second is death, and the third is also death. That's one way to get x equals 2 successes. And these are all the outcomes that we can have. Okay. Now with this or statement, that says I can just add. So I'm going to do the first is DDL. First is death, second is death, third lives, plus the probability of DLD, so just shorthanding this, plus the probability of LDD. Okay. Now, if I want to calculate this first probability, this is the first is death and the second is death and the third is lives. So this and I can do something with an and statement. And that thing that I can do is multiply. So this will be probability of death times probability. So let's do times with a dot, times probability of death again, times the probability of life. Okay, then really I have ands here and here, so I can do probability of death times probability of life times probability of death. Then I can have probability of lives times probability of death times the probability of death. Now, a key step here was this and. And one thing that I can do with the and is that because I assumed independence, it says P of A times P of B is P of A and B. So I used that independence property here, and I was able to get this. Now notice every single term is the same. So this term is the same as this term is the same as this term. So that seems to be 3 times the probability of death times the probability of life. And there's a square here, okay? So if I call P equals to the probability of success, this seems to be 3, and 3 is really 3 choose 2. After all, this 3 right here is this 3 right here, okay? Times P squared. The probability of life, because there's only 1 or 2 outcomes, will be 1 minus P to the first power. Okay, and this is the binomial calculation that we had. Now, let's figure out what this number is. Okay, so if we plug in the numbers, it's going to be 3 times 0.2, that's the probability of death, times 1 minus 0.2 to the first power. Then we can figure out, using our calculator, what exactly this number is. So I'll just calculate this very quickly. So 3 times 0.2 squared times 0.8 equals 0.096, or 9.6% chance that 2 out of 3 mice die. Okay. Now let's figure out if we can generalize this, because I want to figure out a more general calculation. I want to figure out this calculation with 10 mice. Okay. So let's figure this out. So let's see if we can, let's generalize this. So let's, okay, if there are n mice, what is the probability of having x successes? Okay, so I think here 3 is represented by n, and x, that's the value of 2. So if I want to calculate a general probability big X is equal to little x successes, I think I'm going to have n, so right, so instead of having 3, I'll have n, and I'll have x successes times p times 1 minus p. Okay, well p, that seemed to be like an x. So let's replace 2 by the x. Then 1 minus p in our example has the power of 1 on it, and I think we can get that by getting 3 minus 2, or n minus x. After all, there has to be n trials, so we have x successes and n minus x failures. And this is the general binomial formula. So general binomial probability distribution. Okay, and let's use this general binomial probability distribution. Okay, and I like to point out we can use this probability distribution to completely fill in this table. So we figured out that this is like 9.6%. We can use that formula to calculate this number right here, and this number right here, and this number right here. We can calculate the remaining three. Okay, just using this nice binomial probability distribution. Now, one question that students often ask is, when can I use this? And my answer to this is the assumptions. 1, 2, 3, and 4 answer when you can use this probability distribution formula. Because if you don't have these assumptions, you can't use it and you're out of luck. You might have to be a little creative in how you calculate a probability if you don't have these assumptions. Okay. Now let's do a nice little example here, and let's calculate um, calculate the probability x equals 4 mice dying when p equals 20% and we have n equals to 10 trials. That's more typical, is to have at least 10 mice. And I'd still say that's quite small. Mice happen to be cheap to experiment with, and in fact, there are specific companies that have mice for biologists to experiment on. You order a mouse, then you perform your experiments. It's much cheaper than using a human. Okay, so if I want to calculate p of x equals 4 deaths out of 10 mice, I can just use that nice little formula I had up there. That'll be n choose 4 times 0.2 to the fourth times 1 minus 0.2 to the 10 minus 4. Then we just need to use our calculator, so I'll calculate what this probability is really quick. Okay. And I'm getting 0.088 or 8.8% chance that 4 mice die out of 10 when we do this. Now, here's a question that you might ask. Question: how many mice should you expect to die? And here, in order to answer that, they're asking for this, e of x. And this is going to be the summation from k equals, excuse me, instead of using k, I should use x. From x equals no mice dying to all n of them, and I'm going to have x times p of x. We happen to know how to calculate that p of x. So this reduces to this, x times n choose x times p to the x times 1 minus p to the n minus x. And you have to figure out what that sum is. That doesn't sound very nice to figure out what it is. I'm going to give you the answer here. It happens to be n times p. So in this case, if n is 10 and p is 0.2, I'd expect 2 mice to die. Now, in another video, I'm going to go over how to calculate this E of x, the moment generating, and the variance of the binomial distribution. But other questions you might ask is how much variation is there? And here, if you want the answer, I'm going to ask you to watch the next video. Okay. So that is an introduction to the binomial distribution. On the next video, I'll cover its expected value, its variance, and also its moment generating function. Okay.